SwayamPrabha. Digital India. Educated India.
So we'll discuss today again about cellular precipitation in details. You know, when you talk about precipitation, obviously you go back to your aluminum copper system. Precipitation actually can happen in two modes. That's what has been given in the books by Jena and Chaturvedi. As you understand, precipitation actually can happen in one mode. What happen actually, the solids which forms precipitate, which forms directly from a supersaturated solid solution, and taking all the solids from the nearby supersaturated solid solutions and forming a new phase. That is one mode of transformation which is very common, and that is what is seen in aluminum copper, aluminum silver alloys, or copper zinc also. So I will give an example today. But there is another mode of transformations, okay, in reaction, in which the reaction remains same, like alpha 1 going to alpha 2 plus beta, reaction remains same, but alpha 2 and beta precipitates form as a colony instead of separate phase and on the gain boundaries or on dislocations, like in the case of aluminum copper alloys. Here both these two phase, product phases basically forms as a colony of alternative layers or plates of alpha 2 and beta. Overall composition of the colony remains same, it does not change, okay, and that of parent phase, and the growth actually happens, as we have seen in the last lecture also, by the diffusion along the gain boundary. And normally this nucleation of the new phase beta happens at the gain boundary, and it forms, as I said just now, the alpha 2 and beta forms like alternate plates, and then as the gain boundary happens to be the happening place, okay, happening place by I mean to say the short circuit diffusion takes place along these gain boundaries, making the solid partitioning possible. So therefore gain boundary also moves as the precipitates grow, and this is a very different kind of precipitation than the normal precipitation or first kind of mode I talked to you just now. The microstructure looks like a perlite, because perlite also form alternative plates leading to colony formations. That means in case of all eutectoid transformation, this is what will happen mostly, which leads to formation of the lamellar microstructure. But eutectoid transformation, especially in case of perlite, the product phases has completely different crystal structure as compared to the parent phase. Like gamma iron, it has FCC crystal structure, whereas alpha iron, which is a product, plus cementite, which is also a product, have different crystal structure. Alpha iron has a BC structure, Ap3 has a orthorhombic crystal structure. So that is the main difference. But here what happens in case of cellular precipitations, the alpha 2 has same crystal structure than alpha 1, beta may have different crystal structure. So it is more like a precipitation than the what's called eutectoid transformations, okay. Now let us look at some of the pictures. These three pictures, 1, 2 and 3, 1, 2 and 3, they are taken from aluminum copper duralumin, okay, which is the classical precipitation hardenable alloy, and this shows GP zone, this theta double prime, this is theta, as we know that. I do not need to go back and discuss with you again. And you see here that precipitation happens in discontinuous manner in the matrix, okay. It can happen on a dislocation or defects or an Allen boundary, correct. But the cellular precipitation which is shown here in this microstructure, this one cellular precipitation, it is taken from Porter Sterling's book, as you see here that it forms like a lamellar morphology. So, the question is this, the precipitate phase which is here is Mg 11 something, let me just confirm it, what is that, I told you that Mg 12 Mg 17 Al 12 phase precipitate beta, what we call an Mg Al phase diagram, forms like this kind of plates, and in between you have the other phase which is the solutions of Mg, hexagonal solution of Mg. So, alpha, that composition has been adjusted because initially it was a single grain of alpha 1 and then the beta has formed, beta means Mg 17 Al 2 has formed as a black color phase, and because of that solute partitioning has happened. So, therefore, these regions have become solute lean, and the way they form is just looks like a lamellar morphology of consisting of alternative plates. So, this is distinctly different from the conventional first type of precipitation hardening systems. Now, question is this, obviously this kind of precipitation happens by formation of these precipitates on the gain boundary. This precipitate starts forming on the gain boundary, and as these precipitates grow, the leading edge of the precipitates requires solid partitioning, right, because precipitates has a different composition that is as compared to the grain which is supersaturated solution basically, because it has happened, it has formed in a different way which we will discuss with a moment's time. Now, as the precipitate grows requires the solute. So, therefore, it is obvious the gain boundary will act as a short circuit path for this diffusion of the solutes, and thus as the precipitate grows, because more the solid partitioning, more is the growth. So, as the precipitate grows, the gain boundary, it takes along the gain boundary. So, gain boundary also moves, and that is why it is called it is a different type of phase transformations as compared to the normal precipitation. But if you look at even these pictures carefully, normally these precipitates nucleate on the incoherent gain boundaries. Okay. Basically it is initiated by formation of the lamellar colonies at the incoherent gain boundaries. Now, there is a classical example which has been studied by Cyril Stanley Smith, that is copper zinc system. If you look at copper zinc system, which I do not have here right now, copper zinc phase diagram is consisting of several phases, basically alpha, beta, gamma, delta, eta. So, there is a phase called eta, okay, at the end of the phase diagram, and normally solubility of copper and zinc is very low, it is about 2.8% atom percent at about 424 degrees Celsius temperature, and this solubility decreases as the temperature goes down. In fact, solubility will be nil almost at room temperature, and that means this phase diagram, this kind of phase diagram, if I draw this one, this is copper, this is how zinc, okay. So, what happens, there is solubility is decreases, it is just like this way, okay. So, this is a classical picture of precipitation, okay. If once you have such a kind of stuff, let me zoom it up, okay, such a kind of things. So, as the solubility is decreasing, then this is what is signature of a precipitation type of phase transformations in a phase diagram. Now, if we take a homogeneous alloy, okay, it will have about, say, let us say about 2% copper, and then you heat it up to 400 Celsius temperature and cool it down slowly. What will end up is basically precipitates, just like theta or theta double prime precipitates of eta phase in the precipitates of the epsilon phase, not eta phase, into the eta matrix. This is eta basically. So, this will be epsilon plus eta. So, precipitates of the epsilon will form in the matrix of the eta. This is what is routinely seen, and this eta is basically solution of sorry, this is zinc, this is not copper, this will be different because this is zinc, it is an ACP solution, okay. So, now, but if we this happens by diffusion control. Now, if we hit this steel, it is sampled, so about 200 Celsius temperature, I think that is what it is basically heated. No, if the sample is quenched, from 400 to 200, not heated, completely suppose heated up to 400, solutionized, then quenched to 200 Celsius temperature, and then what happened, then this kind of sheets or the plates of the eta phase and solid depleted eta and solid depleted epsilon and solid depleted eta phase will form. Okay, this is eta and this is epsilon, eta epsilon forms. Okay, that's how actually the lamellar morphology comes into picture, and it's obviously starts nucleation of these epsilon phase at the incoherent gain boundaries. That is what is the routine things people have observed, and there is a detailed description of this microstructure in this book. I am not going to go that, but as you see very clearly, cellular precipitation happens at lower temperature, correct, is obvious, because in case of solutionized and aging treatments of even copper zinc system or aluminum copper, aging is done at a high temperature. Even aluminum alloy, aging is done at about 150 to 190 degrees Celsius temperature. If you go back my lectures also you will see that, but here the sample is quenched to a lower temperature. Okay. So if aluminum this kind of thing does not observe, the mode of transformation is not seen, but in case of copper zinc system, as both the mode of transformations happens, so the aging treatment required form this lamellar morphology is much requires much lower temperature. So it happens at much lower, therefore delta G is large and negative. Obviously delta G depends on undercooling. As you cool more, delta G is more and negative. Consequently, sufficient free energy is available for the creation of these interfaces. See, when you have a precipitates like that in a big grain, the interface energy contribution is not that high, because only interface is between the precipitates and the matrix. But on the other hand, you have alternative layers, so interfacial area is large, and interfacial energy, total interfacial energy is quite large. So in order to create such a large interface we need energy. So that is why the bulk part of these free energy available to the system is basically used to create these interfaces, and lamellar morphology reduces. The advantage of lamellar morphology is what? As you have seen in perlite, reduces the diffusion distances. Okay. In fact, for these kind of precipitates to grow, it is basically a lattice diffusion which happens. The atoms diffused from the bulk of the grain to the precipitate's boundary, and then precipitate grows, correct, that is we have seen that. Here that does not happen, basically because the diffusion distance is small, it forms a lamellar morphology just like a perlite, diffusion distance is small, and it happens along the gain boundaries. So therefore these solid, that means lamellar morphology actually helps in reducing these diffusion barrier. Incomplete segregation of solid in the product phase can also reduce the need of diffusion. Okay, also possible that there will be incomplete diffusion segregation of the elements in the product phase, while providing the significant negative energy to drive the reaction. Therefore, three important kinetic parameters for the cellular precipitation are degree of solid segregation, the growth rate, and the interlamellar spacing, because it has this one, so therefore there is interlamellar spacing. There are three important microstructure aspects: the solid segregations, degree of solid segregations, growth rate, and these things. Okay, now question is this, that it always happens, nucleation happens at the boundary between the grains of alpha 1 and alpha 2. Okay, let us do that, it is there in the book, I am just going to describe it, how the nucleation happens. So I will draw some schematic picture. Suppose I have a grain alpha 1 and alpha 2, and this is the gain boundary, and this is the plate which has formed like this is one plate, okay, and this is another gain boundary. So obviously this is the gain boundary again, and this is what is the beta plate. Okay. Now as this plate grows, what will happen? Okay, let me just draw it again. As this plate grows, what will happen? This will kind of create a boundary, at the boundary between alpha and beta phase maintains this one is maintaining certain crystallographic relationship with alpha 1, and obviously it is also maintaining crystal relationship between alpha 2, because you see that these plates has very sharp boundary along these ones. So, that is a coordinate relationship with that. So, interface with alpha 2, obviously the way it is done, interface with alpha 2 is looks like incoherent, and now rate of nucleation of such precipitate is expected to be much more than that of the coherent or semi-coherent particles within the grains, or that of the incoherent particles within the grain boundaries. So, that because of this nature of this kind of things, the interfacial energy between alpha 1 and beta is much less than interfacial energy between alpha 2 and beta, because this is incoherent, and the nature of incoherency tells you that it has a more interfacial energy. So, in order to decrease the free energy of system, grain boundary moves along with beta and alpha 2 interface from one of the edge of the plates to other edge of the plates, so the high energy beta alpha 2 interface is replaced by the alpha 1 beta 2 nucleus. How does it happens? Let us draw it. Okay. So, what actually happens is like this, and it grows. Okay. Right. So, you can clearly see that this boundary has moved up and grown. Okay. This end has moved up and grown. That is what will happen. So, now this will lead to, as this one happens, there is another nucleation possible here at the bottom. Okay. Here let me draw, and which is more easy, and then the other one, this is another beta phase. Okay. Just keeping the view that this beta boundary is carried forward because of that, because this has grown. So, boundary has moved. You can clearly see this boundary which is here, sitting here, this has moved. Okay. It has to move, otherwise it cannot create it cannot allow the beta to grow, and this is how actually these different layers of precipitates grow. And this picture I have shown you, again I am showing you, this is taken from magnesium aluminum system with magnesium 9 atom percent aluminum alloy, which was aged at about 220 degrees Celsius temperature 1 hour, followed by 310 degrees Celsius temperature for 2 minutes. And if you look at the phase diagram, this is this is a typical picture of the precipitation hardenable systems with a decreasing solvus concentration of functional temperature. And so, alpha phase, if you simply heat it at 450 degrees Celsius temperature, then you solutionize and quench at lower temperature, and then you age it, it will form classical precipitates of Mg17Al12 in the alpha. Okay. So, but what will happen is that if I heat it differently, if I simply heat after quenching, if we age at 220 degrees Celsius, that is very high, little high temperature, and then 310 degrees Celsius temperature for 2 minutes, this will lead to such a kind of lamellar precipitates. As you see, this black color thing is basically Mg17Al12, and this one is the solid depleted alpha phase. That is what happens, and the boundary has moved from these to these, and the way boundary has formed is looks like this is grain 1 and grain 2, and obviously with grain 1 the precipitates has coherency, but with grain 2 they do not have, they have an incoherent interface. Now, how do we prove that this is again another picture which I have shown you, but this case of cell has formed at 2 because of aging at 2 temperature, 220 30 minutes and 277 for 30 minutes. Okay, one after that is water quench. You can clearly see there is a cellular microstructure with a certain value of interlamellar spacing. Okay, now question is that one can actually do detailed what do I say, chemical composition measurements or microanalysis of the system using a very high sensitive probe like electron energy loss spectroscopy attached to the transmission electron microscopes, and that is what is shown there. As you clearly see the composition of the matrix, this is alpha 1 and this is alpha 2. Okay. this is again alpha 2. So, as you clearly see in the alpha 1 alpha 2, the compositions of these two phases as far as aluminum concentration is concerned, obviously magnesium will be also same, is almost same within 10 nanometers, correct. Within 10 nanometers there is no change of chemical composition of these phases. So, as the cell front moves, there will be compositional partitioning, okay, because the growth of the precipitates. Now, to be expected that this is expected as since the precipitation is occurring relatively much lower temperature compared to the first mode of phase transformations. So, therefore, the solid transport will happen along the boundaries, okay. Now, one can actually also measure chemical composition, but this tells you that the along the gain boundary only diffusion is happening, because this is alpha 1, this is alpha 2 has been produced from alpha 1. So, beta has grown, okay, in between the large like plates of beta has grown like this, okay. So, because the only way of growing the beta possible is that by solute transport from the alpha 1 and or basically taking the solids, draining the solid up from the alpha 1, and then the alpha 2 will have much lower concentration of aluminum than alpha 1. So, that is happening simply by diffusing these atomic pieces along the gain boundary. This tells you specifically that. Now, one can also look at the concentration of the aluminum or the alpha matrix along these things, okay. If I draw a line S, you see here there is a line drawn. So, there is a Mg12, Mg17Al12 precipitates on both sides, and there is alpha in between, alpha 2 in between rather. So, this is alpha 2, this is beta. So, if you measure the composition, as you clearly see that within the alpha 2 the composition has a gradient, okay. So, this is essentially so therefore, the maximum aluminum concentration in alpha material in the plane. Now, this essentially replica of this similar concentration profile exists within an advancing gain boundary. This must exist, right. Obviously, at the tip of the gain boundary, the compositions of the aluminum, or rather let me draw it and show you. So, this is alpha beta, and then this is alpha, and then there is a beta, right, alpha 2. So, composition is like this. So, that means what? The solids have diffused from the tip of alpha, and this was the gain boundary, tip of alpha along the gain boundary and reach here. This has to happen, otherwise how the beta will grow. So, that is why actually as the solute is diffusing from the alpha 1, which was initially alpha 1, as the alpha 2 forms, basically beta has taken the solutes from the alpha 1, that is why alpha 1 has become alpha 2 basically. So, alpha 1 is having about 9% of aluminum, alpha 2 has about 7% of aluminum. The 2% of aluminum has is partitioned between beta and alpha 2 from the alpha 1, and that happens by the diffusion on the gain boundary. That is what is the most important conclusion drawn from such kind of chemical composition study. Okay, so this is a very not prominently seen cellular precipitations, but it is observed in many systems. That is why I told you, like copper, zinc, aluminum, magnesium, many others, and this tells you another mode of precipitation, not like a parallel Utecht transformation as I discussed with you, which is possible even in the system when you do these different kind of aging treatments, and this allows you to generate different kind of microstructure. So, one can actually play with this heat treatment parameters for copper zinc system or even magnesium aluminum system to create different kinds of morphologies. Cellular precipitation is also discontinuous type precipitation. Why? Because composition of the matrix changes discontinuously. It is changing discontinuously. You see here alpha 1 to alpha 2 is a discontinuous change of composition, it is not continuous change. And this is obviously like other mode of precipitation where the composition of the matrix also change discontinuously from supersaturated solid solution to the normal solid solutions in which precipitates are present. So, therefore, with that actually I like to close on cellular precipitation. So, only thing which I need to discuss with you in the next couple of lectures is the transformation happening in ceramics. Please remember that ceramics also undergo different kinds of phase transformations, and it is not possible because of the time limitation mostly to talk about all kinds of phase transformations happen in the ceramics, and that is why we will discuss only one which is more rather is one of the most important phase transformation observed in systems. So, we will talk about zirconium oxide systems in which this kind of phase transformation do takes place.